Hi Year 12s, it's Mr. Lim again here, talking about equilibrium systems again. Alright, so we are now talking about graphing equilibrium systems. Okay, so if you remember from last video, equilibrium systems are when the rate of forward and the rate of reverse reaction are the same. Okay, so then we're going to show back in graphical form. So we're going to show two different types of graphs, rates and concentration versus time. And then we're going to talk about the stoichiometry considerations when drawing concentration versus time graphs. Alright, so rate versus time. Shows the rate of forward and reverse reactions over time. So what is present at the beginning of the time period determines what rate of reaction is present. So in general, so say you have all reactants, then only the forward rate of reaction will start. Right? And there'll be no reverse rate of reaction because there's simply no products there. Right? If you start all products, then you're going to have only the reverse reaction and no forward reaction, right? And if you have a mix, it depends on whether it's actually at equilibrium or not at equilibrium, but we won't go through that until we get to explaining what the equilibrium constant and stuff like that is. All right. So equilibrium is when both forward and reverse reactions are equal. So what they'll do is they'll overlap each other on the graph. All right. So let's have a look. So here's just rate of reaction. Okay, so let's just assume that there's only reactants. Okay, if there's only reactants, let's just say that this is the forward. This is the forward, and let's just say this is the reverse because it starts at 0. Okay, so if that's the forward, and I'm just going to move that up to 4 just to make it a bit easier. All right. That means that the forward rate of reaction, what's going to happen to that as time goes passes? Is it going to increase or decrease? Well, the forward reaction is going to decrease because there's going to be less reactants over time because all more of it's consumed. Right? So that's going to go down initially. Okay. What happens to the reverse rate of reaction? Well, as some products are produced, the reverse rate of reaction is going to go up. Okay. And that's going to go, forward rate of reaction is going to continue to go down because, well, it is running out of reactants. The reverse rate of reaction is going to go up as well. Okay. And so you'd expect to see that the forward rate of reaction would drop, but it's not going to drop linearly. The reason why it doesn't drop linearly is because there isn't the constant drop of reactants, right? Not only are there simply less reactants and that's going to affect the ratio that can react, but it's also going to be that reactants are being produced by the reverse reaction. All right, so it's not going to drop linearly. It's going to drop in a fashion which looks something like this. It starts out steep at the top, and then it goes and becomes shallower at the end until it plateaus. What does plateau mean? It goes flat, okay, all the way to the end. The reverse rate of reaction will go up and plateau at the same spot. And plateau at the same spot. Okay, so they're plateauing and they're equal and they're overlapping because they're at equilibrium. The rate of forward and reverse reactions are equal, so that's why they're overlapping, and they don't change because the number of particles doesn't change as well. All right, we say that equilibrium is established at a certain point in time, so that's when equilibrium starts. Where does equilibrium start on this graph? It starts at time 10. Okay, because that's where it goes flat. Where it goes flat is the point at where equilibrium exists. Okay, or it starts at least. So this is where equilibrium starts or is established. Okay, now let's have a look at concentration versus time. So concentration shows the concentration or the partial pressure of some or all of the reactants and the products. They can overlap each other, but not necessarily. So let's just let's just, for example, do N2 plus H2 goes to NH3. Right? So that's not a balanced equation, so let's balance that. That becomes a 3, that becomes a 2, and that's balanced. Okay? So now let's go draw these. Let's say that the N2 is the red, the H2 is the blue, and the NH3 is the green. And we're going to say that we're going to start off with some N2. We're going to start off with some H2. Alright, and we're going to start off with no NH3. Okay, so those are our starting points. So let's have a think. As time goes on, the N2, since we start with only the forward reaction, the N2 is going to decrease. So the N2 is going to get lower, 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 until it reaches equilibrium, in which case it will plateau, which is there, so. Alright, so that's what happens to the N2. What happens to the H2? Well, remember, there's only reactants here. I probably should have said that before. There's only reactants at the start. That's why those two are up high, the red and the blue line. And so that means that the amount of H2 is going to drop as well. Okay, so that's going to go down. It's going to go down, 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 until it reaches equilibrium. Now, you should note that equilibrium always is established at the same time for every substance. So therefore, they have to plateau at the same time, roughly at 6 minutes. The NH3 is going to go up, and that's going to plateau. Oops, it's a terrible line. Right, and that's going to plateau also at 6 minutes. And in this example, it overlaps. All right, so we'll show products and reactants. If you start with only reactants, the reactants are going to go down, and the products are going to go up. All right, and then they plateau out. But let's have a think about this, because this isn't actually right. So the N2, there's one molecule of N2 is going to react with 3 molecules of H2. All right. So if I started off with 100 N2 molecules and I reacted them all, how many H2 molecules would I need? I would need 300. That means that the concentration, or the partial pressure in this case, of the H2 should decrease by 3 times as much as the N2. Okay? 3 times as much. And how much has it gone down by here? It's only gone down by the same amount. Right? So that is all wrong. Got to get rid of it all. Okay? Now, so let's say that the N2 goes down by 3 units of partial pressure. So that's 3 units of partial pressure, and let's say that it reaches equilibrium at 4. Okay. If this goes down by 3, or 3, not x, that means that this one, the blue, the H2, has to go down by how many? 9. Okay. So that's 9 squares, which brings it down all the way down to, oops, it's probably not. So we know that this has to go down by 9, doesn't it? Going down by 9 means that we'll end up here at 6 minutes, or not at 6 minutes, sorry, at 4 minutes. Here at 4 minutes. Because that's when equilibrium is established, and we know that it has to go down 9 squares, which is actually 1.8 units. Right? So, if we know that that has to go down by 9, we can mark out the initial point and the final point fairly straightforward, fairly easily. All you got to do is then draw that curve, which is a little bit tricky. Right. And you learn how to draw that curve after a while, and draw and continue. Okay. That's 9 squares. So how much will the NH3 have to go up by? Well, 1 molecule of N2 makes 2 molecules of NH3, which means that for this graph, it'll have to go up by 6 squares. Where's 6 squares? Here. Right. Then you practice drawing the graph. There's that curve, and there's that flat. Okay. You don't need these wings here anymore. And there you have your concentration versus time graph. Okay, that's one example. So this is what we're talking about stoichiometry. You must consider the stoichiometric ratios, which are the coefficients of reactants and products when drawing out the curves. Just mark out the initial and the final points. Remember, so this is at where equilibrium is, and then you just draw the curve as best as you can. Okay, so let's have a look at the next one. Okay, so let's say we're going to show this equation. CH3COOH plus H2O goes to CH3COO minus plus H3O plus. Okay, is this Arrhenius or Bronsted-Lowry theory? This is Bronsted-Lowry theory. Okay, so we know that ethanoic acid is a strong or weak acid. It's a weak acid, so its concentration will be fairly low of H3O pluses. So let's say that we have a 3 mole per liter. Let's put that one in green. We start off with 3 moles per liter of 3 moles per liter of CH3COOH. And we start off with none of this CH3COO and none of this H3O plus. Okay, so this one here, is this a balanced equation? Yes, it is. We know that this one is going to not produce lots of H3O plus. So I'm going to say that, okay, it produces 0.4 moles per liter, and it does so after like 3 minutes. Okay, so it marked out the initial and the final point, and I draw my curve. Okay, the CH3COOH, starting at 3 moles per liter, we should be able to work out how many moles per liter it goes down by. All right, it should go down by how many moles per liter? 0.4, because each box is 0.4. All right, I mean each box is 0.2. So mark out the start, mark out the end, and then draw your curve appropriately, making sure it's flat after the point of equilibrium is established. And the CH3COOH, should there be the same number of that as what? As the H3O plus, so therefore the red one overlaps effectively. Okay, so that's that one there. What happens if I was to also draw on the same graph the reaction between HCl plus H2O goes to Cl minus plus H3O plus. Okay, so we know that HCl is a strong acid. So let's say that it also starts at the 3, right? Let's say the Cl starts at the 0. And the H3O plus, what color should we do that? Let's do that orange. Starts at 0 as well. So, what do we know about HCl? That's a strong acid. So if it's a strong acid, it means that almost all of it turns into H3O plus ions. Okay, so what that means is that the H3O plus ions is very large, almost all of it. So we're going to say like 2.99 is where you go. So you got to draw that curve there. Okay, and then you draw the equilibrium after that. Cl minus, where will that go? That will follow it because it's on the same stoichiometric ratio. And what about the HCl? Where's that going to go? It's going to go all the way down and there'll be almost none of it. Okay, so those are a couple of more examples. Let's try this one here. Okay, the equation is 2CrO42 minus plus 2H plus Cr2 CR2O7 2 minus, and H2O. Okay, now you can't show the concentration of water because it's the liquid, it's the solvent, so therefore you can only show the solutes. Okay, let's just say that we have lots of CR2O7 at the start, 3.6. Alright, and we have no H plus and no CrO4. Okay, so this one, we might show that this one drops by this much. Okay, what's that? That's like 1.6 moles per liter. Right. So how much will the CrO4 2 minus in the red go up by? Well, if that's 1.6, this has to go up by 3.2. So where does equilibrium get established? At time 4 minutes. 3.2 is here. So you go and draw the curve. Okay. And same with the H plus because they're on the same stoichiometric ratio. Alright. So that would be how you would draw that concentration time graph if you started with only CR2O7. Right. Lastly, let's take another one. Let's say N2O4 goes to 2NO2. These are both gases, which means that they have a partial pressure. Alright, let's just say that this one is the blue one, this one is the red one. What shall we start with lots of? Let's start with lots of the blue one. 2.2, and none of the red one. Okay, so this one, let's just say it goes down and establishes equilibrium at 8. Right, and so we say, okay, well, this is going to form equilibrium. Oh no, I've drawn that way too wrong. Right, let's just draw it there. Okay, so that went down by how much? 0.8 or so. So that means the other one will have to go up by 1.6. There's 1.6 and it's over there-ish. Okay, now I haven't drawn that very well. You probably need to do a bit better on the curves and on the plateaus, but that's the general idea. Alright, you've got to take into account the stoichiometry, you've got to take into account what's there, and any changes, which we'll learn about later. If they're made, what happens to them, we'll learn how to draw those in the next video or so. Okay, that's graphing equilibrium systems.